Hello, everyone. I'm Silas. I am a Burrow maintainer, and I'm the CTO of a company called Monax, and a former TSC member. My interests include dancing, cheap wine. I don't know whether you can see the cheap wine in that, but it is in there, and blockchains. And yeah, that's my daughter, the youngest Hyperledger member. So today I'm going to talk a little bit about Burrow. And I'm going to try and convince you of three things. Firstly, that Burrow is boring, but in a good way. Secondly, that Burrow is pragmatic. And thirdly, that Burrow is just enough. And I'm going to study this by looking at the faces of Burrow, which I have named Burrow the Embeddable, Burrow the Sidechain, and Burrow the Cosmonaut. So first of all, just briefly, in terms of what it is a smart contract execution engine, and that's really what it's probably best known for in Hyperledger, although it's not very well known, because we've been integrated into Fabric and Sawtooth, and the Aroha integration is coming. However, we are a full DLT framework. I've put the inverted commas there because I'm never quite sure what framework means, but for the purposes of this talk, we can do pretty much the same use cases that you could do on Fabric or Sawtooth. So we're a complete blockchain solution in that sense. We're also quite old, for blockchain at least. I believe we are the oldest code base in Hyperledger. The original code base was called ErisDB, and was started in, I think, late 2015. Yeah, I'll have a little bit more on that later. So what does we has? We has Tendermint consensus, which is a PBFT style consensus mechanism, Byzantine fault tolerant. We have Ethereum virtual machine for execution. And recently, we have added, thanks to Sean here, WebAssembly for the smart contracts. We have some on-chain governance niceties, and we have increasingly nice tooling, I think. So yeah, what do we want to be? We want to be boring, simple, and fast. I will unpack what I mean by all of these, particularly boring. I also realize that simple and fast risk being weasel words because software is rarely built to be complex and slow. So I'll give a more precise definition for my purposes. For boring, Burrow tries to be predictable in terms of things like performance and latency. It's a pure Go binary. It's fully deterministic in its execution. Tendermint has a novel view change. Well, it effectively avoids view change, so you have a fairly consistent block heartbeat, depending on your timings. And we store a complete rollback history. So for when we encounter an error, we can roll back to the last known good state if we have a dirty write or something like that. And we have forensics tooling for trying to figure out what went wrong. You can also attach the nice Go profiling, which is a feature of keeping ourselves pure Go. We can also define ourselves a little bit by some of our non-features, which, unlike the other frameworks, I guess with the exception of Aroha, we will not have pluggable consensus. It's Tendermint or nothing, and nothing is an option. Actually, I'll come on to that a bit later. And no pluggable execution engine. So we've added WASM now, but we don't have the chain code / transaction processor style arbitrary execution engines. Your smart contracts are written in for the EVM, generally Solidity, or they can be for WASM. We have no single killer feature. Really, the novelty, I think, that we have is in our composition. So, and how we orchestrate the features that we do have. So we have an EVM with deeply integrated permissioning functions. We have the ability to call between WASM and EVM code and native Go functions. We have a fine-grained event stream and an immutable try. We store every version of every height. You can instantly go back to a snapshot. We support ED25519 and SCCP 256K1 keys, which gives us some interop with Ethereum tooling and Bitcoin, kind of, I guess. So boring. Simple. Again, single binary, single code base, single repo, which didn't always used to be the case. We have a relatively small, relatively well-commented, and relatively well-structured code base. So we are a little lacking on documentation, but I think we're relatively easy to understand. Certainly, if you go and try and read Go Ethereum, you'll probably find us easier entry point to certainly to the EVM. We're easy to operate, so we support Prometheus metrics. We have nice configurable logging. We have battle-tested Helm charts and Kubernetes infrastructure, which is what Monax uses to run our back-end system. Burrow likes to borrow, so basically anything that's hard, we get someone else to do it. So that's manifest in Tendermint. Also in our state mechanism, the IIVL try, we use gRPC and protobuf heavily, and a bunch of other nice tooling. We also take the approach that for things that we've found that we need in production, we've favored pulling them into a tightly coupled bundle. So we have this single binary that has a lot of other tooling and even some other services that can run. Fast. So yeah, we're fast enough, which is pretty slow. But the way that we scale is through companion systems generally. So we have a SQL mapping layer I'll talk about a bit later. And there is a lot of room for improvement in the performance, but we generally find that we are fast enough in terms of actual performance. And we have other ways of scaling that I'll get onto. We also fail fast. So Tendermint would rather be off than wrong, and we kind of inherit that approach. So if, like I said before, if we see any problems, we will crash early, and we also have the ability to roll back to previous known good states and put quite a lot of stock in being able to recover. And we're also quick to change. So I'll come on to why I think we're quick to change. I mean that in the code sense. But yeah, this is my slightly hackneyed phrase, my attempt at marketing. This is kind of what we'd like to be, the Redis of blockchain. So the contrast I'm trying to draw there is if you were to look at Postgres or Oracle SQL or whatever, we're not trying to have a huge plethora of features, but we are trying to take an opinion on the features that we do have and to be simple, complete, opinionated, and lightweight. Briefly, just a little bit about history of Burrow. So when the original authors of Burrow, they actually met when a particular Bitcoin whale ran a competition for a decentralized video sharing application. And they thought that Ethereum was interesting. It was pretty early. It was before Go Ethereum existed. And they also thought that this idea of putting permissioning into a blockchain was actually interesting. Nothing like it existed, so we built it. And this was RSDB, a clean room implementation of an EVM with deeply integrated Unix-style permissions for things like call contract, create contract, and some other things related to validation. So, yeah, we believe we were the first permissioned blockchain to market. Correct me if I'm wrong. Tendermint itself used to be a single code base within RSDB. So Tendermint is a popular consensus mechanism and project and public network with quite a large market cap at the moment in the form of Cosmos, which I will talk about later as well. A little bit of a messy divorce code-wise, but in that process, I think some of our engineering boundaries were improved and refined. And then RSDB was accepted into Hyperledger and became Hyperledger Burrow a couple of years ago, 3 years ago, something like that. So what justifies our continued existence is a question I've been asking myself. So from my perspective at least, Burrow provides the shared data and process layer for the Monax platform, which is a legal agreements and obligations management platform, which is built on top of a thing called the agreement network. which is a decentralized legal contract layer, and is based quite heavily around business process modeling notation. So there's a BPMN engine, and that's in a project called Blackstone. We also have various permission marketplaces that occasionally come across my desk. We seem to have a following in cannabis markets emerging in Canada and places. So it's legal tech and cannabis. It's a nice combo. Very interested to hear if anyone else is using us. Please come and talk to me. Yeah, okay, so why should we exist going forward? So I think there is a slight and slightly strange, maybe, apathy in Hyperledger, I could be wrong, around public networks. Burrow really tries to span both the ability to be a kind of public proof-of-stake network, but also to run in a private cloud setting, and even to run in a mode we call Burrow in a box, which I'll talk about, which is almost like more like a Git repo. We think of like Git for law is something that I've played around with. But I kind of subscribe to the idea of connecting private and consortium networks into a series of more public networks, and have the state routing and proof that you can get from doing that. I've also mentioned the business process modeling notation engine we have, which is linked here if you get the slides. I think increasingly Burrow will have first-class support, particularly through WASM, for process modeling primitives. So some of the graph traversal, and we have an eventing system that we can drive stuff off that. Then for the final part of this talk, the third face there, the cosmonaut, I think that Burrow could become the Hyperledger project for Cosmos, which I'll talk about more, but it's an Internet of Blockchains offering, bears comparison to Polkadot. Yeah, this last thing is, I've kind of touched on it, sort of ad hoc state channels. We make it very easy to spec and spin up a network. You could spin that up for a long-running, durable proof-of-stake network, or you could run it for just maybe a system of agreements and then close it down afterwards. You could run it as a single node, no consensus mode chain, and simply just use it to transact kind of offline. You can zip up the Burrow directory and ship it around like a repo. So yeah, it's not internal support for state channels, but it's a kind of state channel-y notion that you can implement using the Burrow tool. Okay, let's get on to the three sections. This is the meatiest part. So Burrow the embeddable. Really what I'll do is talk about some of our features and structure. So first of all, yeah, I put some interfaces up here. I don't expect any plaudits for using interfaces, but they're kind of a symbol to talk around the fact that I think over some difficult refactorings and kind of hard-fought battles with our interfaces, we actually have a pretty nice hackable core. We export a lot of our symbols, and some of this has come from integration with Fabric and with other ledgers, and some of it we've used ourselves to extend things. And it's also, like it's a relatively small code base. So I think that if you wanted to actually extend us in code, it's very viable. Going on from that, we have a clear division of labor. So we've got Tendermint for consensus, IAVL for state, we've got REVM, we've got Perlin's Life WebAssembly engine. And then we have this extendable kernel notion that can deal with supervising things and has various subsystems that you can choose to start or not start. And then we have an extensible RPC layer. Slightly unfair comparison, not entirely apples to apples, but I'll make it anyway. As a software project, our biggest liability is lines of code. And I've touched on it already, I guess, but we have fewer. There are advantages to that. There's advantages to not being constrained by the public Ethereum network. So we don't sit on public Ethereum. We run Solidity, so we have a kind of impedance match with public Ethereum, but we don't run its code. So we've actually been able to trim a lot of fat over the years, and that's one of the things that makes us quick to change. This is a nice little tool, SCC. It has this amusing cost estimate for the development. So apparently Go Ethereum is $500 million, and we're just 3 million. So 24 months. That's nice. Batteries included. So yeah, I just want to talk about some of the things that we package with Burrow, going back to the idea of us including the essentials. We have a range of command line tooling, all built into the Burrow binary. You can download different distributions from our GitHub releases. I can't talk about all of them now, but I'll talk about a few. So Burrow spec and Burrow configure. Spec is a way of templating out a particular type of chain. You can use a spec and you could instantiate new chains from that have the same initial structure. It's not the same as the Genesis, but it's used to make Genesis files. So it's a Genesis template. You can then literally pipe that into Burrow configure, which will give you a full functioning configuration. It will generate keys for you if you want it to, and it will set out the initial token distribution, and you can do some other fun stuff with initial state as well using dump restore that I'll come on to. Then we have a bit of a gimmick here that you can actually run it as a pipe on. This one-liner would give you a single node chain for experimentation. And we like to kind of keep close to the metal, so like no containers required to do this basic stuff. You can even run a multi-node setup with some tooling on your laptop, and that just makes it easier to introspect and debug and understand. We also have some forensics tooling with our Burrow Explore, which allows you to look at both our underlying tenement blocks and our view of history, which is manifest in these execution events, a stream-based view over our state. And then we have Burrow Deploy and Burrow TX. Burrow Deploy is one of the ways that you can deploy contracts and run tests. It has a little YAML mini language that describes the actions it will take. It's a little bit like Ansible. But we also have Burrow TX, which is a more scripting-oriented transaction formulation tool. And you can also push contracts with our JavaScript client, which now has added Typescript, owing to our hipster member of staff and maintainer, Greg, which has some nice features as well. It has Solidity type generation, so it uses the ABIs, these application binary interface files for contracts, and you get strongly typed TypeScript objects that you can manipulate through the contract interface. The contract interface is similar to, if anyone's used Web3.js, you're able to call the functions on your contract, your Solidity contracts, on a JavaScript object. We have our RPC layers all written down in gRPC and protobuf, which also serves as a kind of form of documentation and a kind of like our public, more stable interfaces. So you get a robust RPC layer off that, and we also have them segmented into transaction for writes, execution events for our kind of event sourcing style, fine-grained stream of like what just happened, which is also stored in state. Names provides a kind of DNS-like chain local name storage with a payload that you can attach to that name. And we've got a query layer, and we also have a keys service for key generation and delegated key signing. There's a HTTP interface that you can just curl to see like whether Burrow is on or not as well. We've also relatively recently added a subset of Web3 JSON support, so we can support Truffle and MetaMask. There are some calls that we can't easily support because we're not Ethereum, but the main stuff does work. So yeah, this is something we rely on very heavily. Our SQL mapping layer is called Vent. And what it does is it listens over our execution event service for Solidity events. And then you have a declarative mapping specification like this that says, take this, this matching field on an event and route it to this table in this column. Now what this allows us to do is, I mean, I think most real blockchain use cases end up building something like this, at least in an ad hoc way. But what this allows us to do is to write a traditional web app and API service, and then we use Vent to map into view tables. And then we have some synchronization helpers around that that allow you to expose that as a single system illusion. And it means that you can use a much more traditional stack above the blockchain. So we use Postgres. It supports Postgres and SQLite. Okay, so dump restore. Yes, this is slightly sacrilegious. So this is essentially Git rebase for blockchains, which of course does kind of nullify the immutable tamper-resistant log element of a chain. However, I believe we can be excused on this because the way it actually works is when you create a new genesis, you're effectively forking the chain. We lock in the hash to the state root at the height we forked. So if you hang on to the old chain, you can follow the chain of chains, and essentially the integrity and authenticity is preserved in that way. But what this crucially allows us to do, and this is extracted from real actual use, is this is still an immature technology relatively. We need to make breaking changes to not accumulate unmanageable levels of cruft. We also made some changes where we would run up like a gigabyte a week. We cut that by a factor of like 100 or something, 1,000. We wanted that benefit. So we've done various upgrades on the agreements network and with the Monax platform, and this is what's allowed us to do it. Going forward, we'll do that less, but like I say, we can hang on to the previous chains. It also has some more interesting uses outside of just backup and recovery, in that you get a JSON representation of the core state. So it doesn't store transactions, it stores the resultant state in the Ethereum worldview, so address bucketed by address and some other metadata. You can hack on that to do some kind of interesting things. So you can filter or transform it to import it into another system, kind of like an ETL process. You can also, and this is something we probably will want to support with our governance primitives that I'll come on to, you can deliberately fork some of the state. So for example, take the agreements network. Maybe I've got a system of agreements. I want to go and transact on them in private. Now, I don't want to bring all the other agreements. I could extract them using this mechanism. And I'll come back to the governance point in a second. The other thing is with GDPR, the data protection law in Europe, and with other data protection laws around the world, sometimes you may need to redact personal information you've stored on chain. Maybe you need to then adapt your data model so you don't store that, but it can happen, and it's something that we've had to use. Just to show you some usage, so this is dump restore in action. So the first line says, dump me this chain, remote chain at height 1337. Then the configure call takes in that dump state, calculates the hash, takes the original genesis, inserts the hash into the new genesis, spits out a config. The restore call then loads that into the state trie, and then Burrow start spins the whole thing up. Which brings me on to part 2, which is Burrow the sidechain. Probably the bit I'm struggling to give a clear message around, but I'll have a go. So sidechain, for my purposes, are about state being stored somewhere else. So that could be a database, it could be another chain, it could be a blob store. And the idea that you use the sidechain to track and prove that state stored elsewhere. So, in our case, we have certain interactions that are legally manifest around acceptance, approval, consent, signatures. We're tracking those in a chain that relates to data we store in our Postgres database and our other systems. There's also something in this kind of generalized idea about sidechains about like extrinsic incentives. So in the case of a proof of stake chain, you've probably placed a bond on a public network that could get slashed. In the case of, say, the food safety use case that was raised in the keynote this morning, you're compelled to cooperate to be legally compliant. So I think that with Burrow, there's a way of looking at this kind of sidechain idea that goes through various different scales. So Burrow in a box that I mentioned before is this idea that put it on a thumb drive, copy the Burrow repository, share it with your friend, let them go and do some signing task, share it with someone else, like pass it around on a thumb drive kind of idea, embed it into a API service so that you can run the same process modeling logic that you would run in a more public setting. We can go up another level into like the private cloud. So like it's not a completely insane solution to use something like Burrow. It's what we effectively kind of do as a sort of Zookeeper or etcd alternative. So those are fault-tolerant systems that allow you to do service discovery and synchronize your private cloud. We essentially have Burrow running there that gives this regular heartbeat in the form of the height and is Byzantine fault-tolerant. And that can be a good thing, particularly if you don't trust your developers. Layer 2 scaling is the probably more traditional understanding of sidechain. So this is the idea that the transaction throughput on something like Ethereum or Bitcoin is very low. If you want to run some Ethereum smart contracts that are quite intensive, you're better off having some anchor point on the public chain, like the validator hash that is regularly updated. Run your contract on the layer 2 chain, on the side chain, and then inherit some of the security benefits of the public chain onto your private or layer 2 chain. You're going up kind of not necessarily mutually exclusive, but public proof of stake networks that I've mentioned. And then the kind of the uppermost level of this is the multi-chain world. So this relates to the final bit of the talk on Cosmos, but this idea of state routing between chains that are connected. Just a kind of an observation from dealing with legal agreements and starting out with a more public notion and going into what is a more private platform, is we found that actually by modeling our shared data as if it were public, there are certain benefits, even if it's private. So you get this strong cryptographic audit log. You're able to kind of think about your user-level shared data, so the other counterparties to an agreement, as distinct from your billing organization, profile information. So there's a way that it kind of cuts out the noise, and you can kind of, it's a way of kind of segregating your data model. And then ultimately, the same code can then be ready for a public spin-out, which is probably what's going to happen with the Monax platform, our proprietary offering, and the agreements network. We'll probably have a separate public zone. Talk a little bit about governance. So if you want to run certainly these public permission networks that ultimately are beholden to no single authority, we have a number of governance mechanisms. So tendermint validators are given the right to validate by holding a bond. So Burrow has a native token. Their voting weight is in proportion to how much of that token they have. So we have a system around allowing validators to come and bond. They need a bonding permission to do that. And now there's a lot of ways that you can grow your network. You could have proof of authority, fixed validator set, preordained. You could have a single authority that has a kind of root permission. You could have a autonomous contract, which is the only thing that has these bonding permissions, and implement some autonomous process to allow validators to join. You could have invite only. Burrow supports all of these for a mixture of these mechanisms. So like in the case of GovTX, you can grant that to a human user, or you can grant that to a machine. If you grant GovTX to a machine, then it's only that systems contract, like process one, that can make the changes. We also have an identification layer that is about bootstrapping a network. So it's about securely adding other validators, friends of friends type viral kind of public network. So we have also an on-chain API service, which really helps Burrow be self-contained in these kind of more decentralized use cases. This is something that other Ethereum chains don't have, to my surprise. But you need these little binary files, or these binary description files, in order to talk to Ethereum chains. It's a pain if you've got the wrong one. Burrow now will store them when you deploy the contract, and you can pull down the ABIs that are definitely the right ABI to that contract. We've also got metadata, so you can actually ask the contract, what the hell is at this address, this random bytecode, what is it? And we also use it in our event service to synchronize with our mapping layer. ABIs can also be used for code generation. This is something that we'd like to have as a kind of future feature so that you can have a more simple-minded API for calling functions. Rather than having to bit pack in your client and then send that, Burrow is able to introspect and have other reflective possibilities on the contracts that it is storing. Much friendly calling and introspection. I have no idea what I was thinking when I wrote that. Let's gloss over. Keys service. So there is a keys service that can act as a delegate for signing transactions on your behalf. This is something that we use in the Monax platform, in that we have a hot wallet, which is a user proxy, and our API is authorized onto that hot wallet, a bit like SSH keys, and our API uses this delegated signing. If you then wanted to take control unilaterally of that user proxy, you could do, and then you would be signing your transactions at the edge. But we have a key service that allows you to do this delegated signing, and it also powers the Web3 API too. So finally, this is a relatively brief section on Cosmos, but Cosmos is an Internet of Blockchains project, not massively dissimilar to something like Polkadot. It's come out of the Tendermint company, and it defines a set of specifications, which I link in the next slide, that describe how you should escalate a transaction that you would like to go to another chain. So the idea here is that you only pay for the interactions you care about. So on your supply chain, you run your day-to-day transactions. If you then need to send some information to, say, an agreements network, that's when you send an IBC packet, very similar to it's analogous to packet routing on the internet, that can then go onto the other chain. Now, you have cross-validation, and you can give a hierarchical proof across this routing web of chains. And then the other idea that is that you price interactions you care about as well. So you can have some internal token dynamics that apply to zones that give some flexibility. So this is still something that is a work in process, but the Cosmos public network, the main net, the original hub, is up. And they're also currently running a thing called Game of Zones linked at the bottom there, which is a competition for some amount of Atom, which is the Cosmos token that you can win for setting up an interesting zone. So yeah, Cosmos is happening. Burrow will support it, and we'll actually be ready for it in the sense that we have this long history with Tendermint. We're quite well placed to ride that wave with Tendermint. So in conclusion, we are boring, but we are also interesting. We are utilitarian, by which I mean we include features where we've seen a need. We are willing to have a little bit more of a monolith in service of that ideal. We are ambivalent. So we're ambivalent to public, private, cloud. We are ambivalent to Ethereum or Cosmos. We are ambivalent around a synchronized full network, or even running a single node, no consensus, local repository. And we're ambivalent around proof of stake, proof of authority, or even a benevolent dictator. So I think we have what it takes to deploy a practical blockchain. And you should join us. You certainly can help us. We have a lot of bugs and documentation that could be worked on that are good starters. Well, not a lot, a few. And also, I think that you should help us. You may be needlessly sweating to configure something that we've already built, or that you could fairly trivially extend to a different use case, and hack on Burrow. And finally, if that doesn't persuade you, I thought I could just end with a vague threat. So yeah, what else? Thank you very much. Just before I end, and have some questions if there are any, I just wanted to signpost a couple of other Burrow talks, 2 other Burrow maintainers here. One is tomorrow at 3 p.m., which is about a very interesting development called Solang, which is a Solidity to WASM compiler that Sean has been working on, and its relationship with Burrow. And then Greg is running an interesting workshop on Friday that will be something to do with crypto marmots. So you won't want to miss that. Yeah, I've got another slide of contact information on here if you want to download the slides, but I'm going to go back to that because I quite like this page. Cool, thanks. Yep.
How does Burrow scale in various types of situations? Like how distributed is it, or what are the bottlenecks of the system?
So we have, you're dealing with the worst case n-squared message complexity with PBFT style networks. So the approximate saturation for a network is 100 to say 300 nodes. So take Cosmos. Cosmos currently runs with 100 validators. So the way they have it is the top 100 staked validators get to actually be validators. You can have a lot more nodes on the network that take part in gossip and improve connectivity, but it's those top 100. They're going to add validators until a maximum of 300. Once you get to that, you can get reasonable speeds and throughput, but the way to scale it after that is Cosmos. is to have this is to have a hierarchical scaling. So you need to have various hub networks, and in principle, that ought to scale very well in the way that a tree will scale. We could do with some more precise numbers. Tendermint do have some, but without talking about methodology, they're often kind of nonsensical. So I'd be interested in getting some stronger benchmarks, but right now we've kind of got bigger priorities, I guess, with a small team. But. Dan.
With your ability to snapshot state, can you snapshot subsets of state space?
Kinda. So, yeah, we have a thing called the mutable forest, which was fun to name. That does kind of do that. That maintains a bunch of separate IAVL tries. But we have a separate one. It still lumps together all accounts. Names are done separately, so not an arbitrary slice of state. I have had thoughts about replacing the state mechanism for a kind of prefix tree that would allow you to do that sort of thing. But yeah, no, we don't right now. So we have a separate storage tree, account tree, names tree, and stuff like that. But yeah.
Okay, so when you do snapshot state and you want to tinker with it, did you say are there tools to go and tinker with?
So when I was talking about the tinkering with state, yeah, it'd be like JQ. So in terms of dumps, you can manipulate that JSON dump, and that's about forking a chain. For manipulating, we don't have tooling for messing with the actual runtime on-disk state.
But if you dump it, you're dumping it to JSON, so you can just be
you can mess around with it that way. Yeah, and depending on how you would design your contracts, if you've got you want to take out a particular agreement or a particular user, that will be a singular addressed thing if you're lucky, unless you have it in a bulk contract. But yeah. Yes.
I just want to make sure I was clear. So your plan is to support IBC protocol inside Burrow?
That's the plan. Yeah. So Greg has done the early work on this. So they have, if you look on somewhere on here, I have a link to the spec there. So that's still under somewhat active developments. They had a white paper that came out quite a few years ago. They've got the hub chain that is now running. They also have their own SDK that you can check out. But they are finalizing exactly how the IBC packet will work. I think there are test nets up. It's meant to be ready pretty soon, the spec, and then we will try and get around to implementing it. Yep.
Sorry, this is a very basic question, but what does the schema look like, or what's the data look like when it's stored in Burrow? Is it kind of like Sawtooth, where it's kind of like a very leaky kind of complexity, where you really have to understand the binary structure of the data to read it or understand the data? Or is it more like encapsulated or SQL-ish, or what's it like?
All of those things. Yeah, so, okay, so the basic storage is we're using go-level DB as a node store in our tree. All of our core objects, like our account storage objects, are protobuf encoded. So in that sense, if you can walk the tree, which is IAVL thing, then you can decode in protobuf. But IAVL is, I guess, relatively opaque if you're not that library, not hugely complex. So there's some transparency there. In terms of schemas and walking stuff, that's really what Vent is all about. So Vent listens to this stream of events, which you could listen to kind of works a bit like Kafka or something. It listens to these stream of events and it kind of materializes them into the tables. So the way to get a nice schemaful view on it is just use the SQL. So you have to define your mappings, and you have to. It's kind of it's quite neat how it works. It's kind of also kind of a hack because Ethereum, but you set up certain events which you can declare in your contracts, and then you have it's a solidity event relational mapping. So that would be the best way for analytics to poke around. But over the RPC, the core types that we can stream to you, you can use that with any gRPC client, any protobuf client to decode that. think, was there another hand up somewhere? Same time, maybe not. Okay, thank you everyone.